Hello, this is Dr. Vev. One more energy video. What we're going to do here is interesting. Previously, you've solved the Atwood machine using free body diagrams and Newton's second law. We're going to try to repeat the same derivation, but only using ideas from work and energy. So let us start by considering the system. It's got two masses attached with an ideal string going around an ideal pulley. The ideal nature of the pulley means that it's got no mass and it's completely frictionless. Due to that lack of friction and the fact that the string doesn't stretch and the support point is also fixed, we can write the non-conservative work equals 0. That is really the first step before we can use energy conservation. Now it's actually easier to use energy conservation in the form of changes. So the change in the kinetic energy of 1 plus the change in the kinetic energy of 2 plus the change in the potential energy of 1, gravitational potential energy of 2 is equal to 0. That is the statement that energy is conserved. What we can now think of is one of the masses is heavier than the other, so let's suppose that m2 is heavier than m1. So it's go down by a distance y, that'll go up by the same distance y because the string is not elastic. Also, it'll have the same velocity for the same reason. So we can simply denote the velocities by v. Therefore, assuming the system starts from rest, the change in the kinetic energy is just the kinetic energy. So it's going to be 1/2 m1 v squared plus 1/2 m2 v squared. Now the gravitational potential energy of 1 increases because you're going up a height y. So it's going to be m1 gy. And the gravitational potential energy of 2 is going to decrease. Now this is the reason I favor the change formalism. So you don't have to define a reference for potential energy. You can just keep track of the changes. And the potential energy of 2 is going to decrease because it goes downwards. So it's negative m2 gy is equal to 0. So I'm going to transfer things over to the other side. So 1/2 m1 plus m2 times v squared is equal to m2 minus m1 times gy. That's a beautiful expression because it immediately gives us the square of the velocity. It is m2 minus m1 divided by m1 plus m2 times 2gy. Let's save this expression. It is not our final result yet, but it's a worthy result to box because the square root of this is just the speed of the system, and it's an important thing to know. But however, acceleration and tension are the two things we want to find. Once you have the speed, how do you find the acceleration? The answer is to differentiate both sides. So let's differentiate both sides of this boxed formula. So if I differentiate velocity squared, I'm going to get 2 times the velocity times dv by dt, which is the acceleration, is equal to, so that's differentiating, m2 minus m1 over m1 plus m2 times 2g times dy by dt. Well, dy by dt is just the speed again. I can cancel the speed on both sides, the 2 on both sides, and I immediately get the acceleration of the Atwood machine. m2 minus m1 over m1 plus m2 times g. So that's the traditional Atwood machine acceleration. Beautiful. Now, up to this point, I believe anybody could have carried out this process one way or the other, but the next part is sure to stump most people. How would you find the tension? You see, tension is a kind of a difficult thing to find because tension is an internal force. It's an internal force to the system. Energy doesn't really see it because it's internal. So to see it, what we need to do is we need to split the system. Meaning we look at either the mass m1 or the mass m2 by itself. I will choose to look at the mass m2. Let me draw a picture, and I'm not going to call it a free body diagram because we're not doing Newton's second law, so I'll just call it a picture. Well, in this picture, you're going to have the force of tension acting up and the force of gravity acting down. Well, all right, it is the free body diagram. Why be shy about it? But I'm not going to write Newton's second law for it. I'm only going to use the work energy method. So that's the velocity y, and that's the displacement velocity v, and that's the displacement y. So we have to use the work kinetic energy theorem and nothing else. But the work kinetic energy theorem for this mass m2 goes as follows. The sum of all the works done on this mass is going to be equal to the change in the kinetic energy of just that mass. So from systemic application of work energy theorem, we are going to a specific application of the work energy just for the one object. Now this drags in forces because the work done by the force, so there are going to be two works done. One is the force of gravity dotted with displacement plus the force of tension dotted with displacement, and the change in the kinetic energy is just 1/2 m2v squared. So that's great. By this process of dividing the two masses, I've been able to finally find out tension for the first time. Now, gravity and displacement are in the same direction. So the main purpose of drawing this figure is to just see where all the arrows are pointing. Fg and y are in the same direction. Ft and y make a 180-degree angle. So the dot product, which involves the cosine of the angle, can now be calculated. So I get m2g times y times cosine of 0 degrees plus ft times y times cosine of 180 degrees is equal to 1/2 m2 times v squared, which is all of that. So I see that my 2 cancels out. That's an mgy, m2gy, and I also have an m2gy on this side, so I can subtract, and I'm going to get ft times y, cosine 180 is -1, is equal to, I'm going to get m2gy, and as common factor I have m2 minus m1 divided by m1 plus m2, and because I take this to the other side, I'm going to get a -1. This can be simplified using common denominators, so let's do that. So I get negative fty is equal to m2 gy times m2 minus m1 minus m1 minus m2 divided by m1 plus m2. Observe, m2 cancels out, so I get -2 times m1 in the numerator. Negative ft times y equals -2 m1 m2 over m1 plus m2 g times y. Let me cancel the negative sign on both sides and the y on both sides, and I end up with the amazing result that the tension of the Atwood machine ft equals 2m1 m2 over m1 plus m2 times g, which also is the actual result. Now, in case you're wondering how the original Atwood machine results were got, let's just quickly do that. We can draw the free body diagrams for, so this is just to show people that these results are actually what you expect. I'm going to quickly solve the problem. So for mass m2, since it's going down, I'm going to get m2g minus f sub t equals m2a. For mass m1, since it's going up, I would get ft minus m1g equals m1a. Now when you add these two together, ft cancels out, so I get m2 minus m1 times g equals m1 plus m2 times a. And when I divide both sides by m1 plus m2, I get that formula for the acceleration. So that's how the acceleration works out. Now what about the tension? Once you find the acceleration, you can of course put the acceleration there and solve for tension, but that will lead to awkward things like that. So what I want to do is something else. I'll multiply the first equation by m1. So I'm going to get m1 m2 g minus m1 ft equals m1 m2 a. Actually, how about if I multiply the first equation by negative m1? So that becomes that. The second equation I'll multiply just by m2. So I get m2 ft minus m1 m2 g equals m1 m2a. Now I'll add the two equations. That's pretty much what I did there also. When I add these two equations, the right hand side simply cancels out, and I end up getting m1 plus m2 times ft minus 2m1 m2g equals 0. And you can see that when I solve for f sub t, I'll immediately get that. So the Newtonian second law analysis, which by the way is much shorter and much more elegant than the energy method in this case. So Newton's second law does have its moments, but in a world where the work energy theorem is all you know, you can still get every result that you got using Newton's second law.